Every second of your life, light is entering your eyes. It slips quietly through the room, reflects off walls and skin, bends through lenses and fluids, and finally becomes vision. It feels familiar, harmless, almost invisible in its importance. And yet, hidden inside this ordinary experience is one of the strangest facts in all of physics. The thing delivering all this information may not actually have an inside at all. Photons, the fundamental units of light, appear to possess no internal structure, no measurable size, no layers, no core, no hidden machinery ticking away beneath the surface. According to everything we can currently test, they behave as if there is nothing inside them whatsoever. And still, they carry energy. They carry momentum. They warm your skin, trigger chemical reactions in your eyes, and travel across the universe for billions of years without falling apart. That contradiction is where our journey begins. In this series, we are not rushing toward answers. We are slowing down. Let your breathing settle. Let your shoulders relax. This is not a race through equations or a parade of facts. It is a quiet walk through a mystery that physicists have been circling for more than a century. Tonight, we begin with the most basic question of all. Does light have any internal structure, or is it truly as empty as it seems? To understand why this question matters, we need to compare light with things we know far better. Take an electron. Electrons are often described as point-like, but they still reveal internal properties when we probe them. They respond to magnetic fields. They possess charge and spin. When accelerated, they radiate energy in specific, predictable ways. All of these behaviors hint at an underlying structure, or at least internal degrees of freedom that can be manipulated and measured. Photons behave differently. When physicists attempt to probe a photon in similar ways, the usual clues simply are not there. Photons have no rest mass. You cannot bring one to a halt and examine it. You cannot peel back layers or scatter pieces off a hidden core. Every experiment we have devised, from tabletop laser setups to massive particle detectors, points to the same unsettling conclusion. Photons act as if they are fundamentally structureless. This is not a matter of technological limitation. It is not that our instruments are too crude. Some of the most sensitive measurements in human history have been aimed at light. We observe photons that began their journey near black holes, photons that crossed expanding space for billions of years before brushing against a detector on Earth. These photons pass through magnetic fields, gravitational wells, dense clouds of plasma, and vast regions of near-perfect vacuum. And still, they arrive intact, not frayed, not altered, not revealing any sign of an internal composition being disturbed along the way. If photons were made of smaller parts, we would expect those parts to leave fingerprints. We would expect scattering patterns, delays, energy losses, or distortions that betray an inner complexity. Instead, light behaves with a stubborn simplicity. It either arrives or it does not. It interacts in discrete moments, and between those moments, it offers us no handle to grab. This leads us to a subtle but crucial point. When physicists say that photons have no internal structure, they are not making a philosophical claim. They are making a practical one. Structure, in physics, is something you can interact with, something you can excite, rotate, compress, or deform. For photons, there is nothing to manipulate in this way. There is no experimental knob that reaches inside a photon and turns. Even gravity, which bends the path of light across the cosmos, does not appear to disturb anything internal. A photon grazing a massive galaxy cluster curves smoothly, following space-time itself, not because its interior is tugged or twisted, but because the space it moves through is curved. The photon behaves less like a tiny object and more like a perfectly obedient messenger of geometry. This raises a deeply uncomfortable question. If photons have no inside, what exactly is moving when light moves? When a wave of light oscillates, what is oscillating? When light carries energy, where is that energy stored? These questions feel almost childlike, and yet they sit at the frontier of modern physics. For now, we resist the urge to answer them. Part 1 is about establishing the mystery, not resolving it. Light appears to be real. It does things. It changes the universe. But it does so without revealing any internal substance in the way matter does. It is as if nature has given us an entity that behaves like something while refusing to be made of things. This realization should not make you uneasy. It should make you curious. We are standing at the edge of a concept that forces us to rethink what it even means for something to exist. In the next part, we will take the next careful step forward, asking what could possibly be vibrating, rotating, or carrying energy if there truly is nothing inside a photon at all. In everyday language, we often say that light vibrates. Diagrams show neat sine waves rippling across space. Arrows indicate electric and magnetic fields oscillating in perfect rhythm, perpendicular to each other and to the direction of travel. But there's a deeper problem hiding beneath this metaphor. If photons have no measurable size, no internal moving parts, no physical thing to deform or stretch, then what exactly is doing the vibrating? This is not just a philosophical puzzle. It's a fundamental tension between our intuition and the mathematics of the universe. Let's begin where classical physics left us. In James Clerk, Maxwell's elegant equations, light is described as a self-propagating oscillation of electric and magnetic fields. A changing electric field produces a magnetic field, which in turn produces a changing electric field, and so on. The result is a wave that moves through space at a precise and finite speed, the speed of light. But even in this classical view, there's a subtle clue. Nothing material is waving. These aren't strings or particles bouncing back and forth. They're fields, invisible quantities defined at every point in space, capable of storing and transferring energy, but not composed of matter in any traditional sense. So when we say light vibrates, we're really saying something else. The values of the electric and magnetic fields are changing over time at each point along the wave's path. That's the motion. That's the rhythm. It's not a particle shaking up and down. It's a region of space where fields are undulating. This already feels like a departure from what we know. In most of our experience, motion is a property of things, cars, atoms, winds, waves, in water. But light does not need a medium. Its motion exists even in absolute vacuum. It's not something that needs to shake. It is the shaking. Yet even this classical picture breaks down when we move into the quantum realm. A photon is not simply a little wave, nor is it a chunk of matter. It's a quantized excitation of the electromagnetic field, meaning it is the smallest possible ripple that still carries energy. This ripple doesn't gradually fade in or out. It exists in discrete units. You cannot split a photon in half. You cannot dial it down. It either exists or it doesn't. Here's where things get more surreal. We often imagine the photon as a tiny bullet of light, a particle moving through space, but this is a metaphor borrowed from a simpler time. In reality, a photon behaves more like a pattern. It doesn't have a position in the way a marble does. It has a probability distribution. Until it interacts with something like a detector or an atom, it is smeared out across a range of possibilities. So, again, the question arises, what, if anything, is vibrating? In quantum electrodynamics, the field itself is the object. The photon is a spike in that field, a compact, indivisible flicker. There's no inner motor turning, no sine wave sloshing inside a shell. What we call vibration is actually a change in the configuration of the field, moving forward in time, propagating outward from the point where it was created. But to the human mind, this still feels unsatisfying. We want something concrete to hold on to. We want to ask, what is it made of? Imagine an antenna broadcasting radio waves. The electrons inside the antenna accelerate, creating disturbances in the surrounding electric and magnetic fields. These disturbances ripple outward at the speed of light. As they travel, they aren't composed of electrons or atoms. They are composed of field behavior patterns in space. They carry energy, momentum, and angular momentum. And if the broadcast is configured precisely, those patterns can be concentrated into individual photons. Now, Zoom in. Think of a photon not as a ball of energy, but as a self-contained packet of field activity. There's no structure inside the photon. There's just the field itself behaving in a specific way over a finite region for a finite time. This is why photons can exist in perfect vacuum. There's no substance required, only the field and its laws. No aether, no carrier fluid, just empty space, alive with possibility. Let's return to the question again. What vibrates when light vibrates? The answer is not a what. It's not a thing. It's a how. It's how the electromagnetic field evolves over time. It's the relationship between changing electric and magnetic components. It's motion without moving parts, form without substance, action without actors. This makes the photon one of the strangest players in all of physics. It is pure behavior. It cannot sit still. It cannot be broken down. It cannot be opened or hollowed out. It is what happens when the universe expresses energy in its most minimal, elegant, and untouchable form. And yet, this strange ripple of nothingness can knock electrons off metal surfaces. It can burn your skin. It can be aimed with surgical precision in a laser. It can carry your voice across oceans. It can form the image of a galaxy on the mirror of a telescope. It does all of this without ever revealing what it's made of. So in part 2, we've uncovered something profound. When we speak of light vibrating, we're not talking about a thing shaking, we're talking about a pattern expressing itself. A pure excitation. A dance that exists only as it moves. But this revelation only deepens the mystery. If there is no object and no interior, how can a photon have spin? How can something without volume or edges still carry angular momentum? In part 3, we'll slow down again and ask, what does spin even mean when there is no body to spin? At first glance, the idea seems absurd. Spin, in everyday language, is rotation. It is something turning around an axis. A planet spins, a wheel spins, an ice skater spins faster by pulling her arms inward. All of these examples share one basic requirement. There must be something there to rotate. A body, a shape, a distribution of matter, with parts that move relative to one another. And yet, photons have spin, not metaphorical spin, not poetic spin. Real, measurable angular momentum. Photons can transfer spin to atoms. They can twist microscopic particles. They can even exert torque on objects when absorbed or scattered. This is not a mathematical trick. It is an experimental fact. So we are forced to ask a question that sounds almost nonsensical. How can something with no size, no surface, and no internal structure still spin? To approach this carefully, we need to unlearn a powerful intuition. Spin, in quantum physics, does not mean spinning like a top. This is one of the most misleading coincidences in scientific language. The word spin survived from early attempts to visualize quantum behavior, but it no longer describes a literal motion in space. When physicists say a photon has spin, they are not imagining a tiny sphere twirling as it flies. They are describing a specific, quantized property of how the electromagnetic field behaves. Photons have a spin value of 1. This number is not arbitrary. It tells us how the photon's field transforms under rotations. It tells us how the phase of the electromagnetic wave changes when viewed from different orientations. And most importantly, it tells us how light interacts with matter. To make this clearer, consider polarization. When light is polarized, its electric field oscillates in a particular orientation. It might swing up and down, left and right, or trace out a circular pattern as it propagates forward. Circular polarization is especially revealing. In this case, the direction of the electric field rotates as the wave moves, forming a helical pattern through space. This rotating pattern carries angular momentum. But notice what is rotating here. It is not a physical object. It is not a surface. It is not a rigid structure. It is the orientation of the field itself. The spin of a photon is encoded in the geometry and symmetry of the electromagnetic field, not in the motion of material parts. This is the key shift. Spin is not something a photon does. Spin is something a photon is. The photon's spin arises from the mathematical structure of the electromagnetic field. The field has built-in rotational properties. When these properties are excited in a quantized way, we observe them as photon spin. There is no hidden core rotating inside the photon. There is no internal axis. There is only the field, extending through space, expressing angular momentum through its configuration. This explains something subtle and profound. If photons truly had an internal structure, a little spinning body inside, we would expect contradictions. A rotating object should have a surface velocity, but a photon always moves at the speed of light. If it were spinning like a solid object, parts of it would need to move faster than light to keep up. That alone would violate relativity. Nature avoids this problem elegantly by never giving the photon a body to rotate in the first place. Instead, angular momentum exists without rotation. Spin exists without spinning. The universe keeps the effect while discarding the mechanism our intuition demands. This is not unique to photons. Electrons also have spin, and they too cannot be pictured as tiny spinning balls. But photons push this abstraction even further, because they lack rest mass and cannot be localized in the same way matter can. For photons, spin is inseparable from motion. A photon's spin is always aligned with its direction of travel. It has no option to spin in place. It cannot stop and rotate. It only exists while moving forward through space-time. Once again, we see the same pattern emerging. Photons do not possess properties in the way objects do. They are properties of a field, momentarily concentrated, briefly interacting, then disappearing. This realization forces us to confront another uncomfortable idea. If spin does not require an internal structure, if energy does not require mass, if vibration does not require a medium, then perhaps our demand for what it is made of is the wrong question entirely. Photons may represent a different category of existence, not things built from parts, but events, not objects, but processes, not matter, but action. And yet, despite their lack of substance, photons are remarkably effective. Their spin can encode information. It can determine whether an atomic transition is allowed or forbidden. It can influence chemical reactions and biological processes. Life on Earth depends on photons with very specific spin and polarization properties interacting with molecules in very specific ways. All of this power, without an inside. At this point in our journey, the mystery has sharpened rather than softened. We have learned that photons are not tiny objects. They are quantized expressions of a field. Their vibration is not motion of matter, but evolution of patterns. Their spin is not rotation, but geometry. So the question shifts again. If photons are this simple, this stripped down, could they be rearranged? Could light itself be folded, curved, or looped into something more complex? Could matter, at its deepest level, be built from light shaped in extreme ways? This idea may sound speculative. It may even sound dangerous, but it has tempted physicists for generations. In the next part, we will carefully explore one of the most intriguing and controversial ideas in theoretical physics, the possibility that particles like electrons might be understood as light trapped in a closed path. Not as a claim, not as a conclusion, but as a question worth slowing down for, because if true even partially, it would mean that light is not just something that illuminates the universe. It may be something the universe is built from. Up to this point, we've explored light as something deceptively simple, a ripple in the electromagnetic field, indivisible, without mass or structure, yet somehow capable of carrying energy and spin. But now a strange possibility begins to surface. What if light could become more than what we think it is? What if, under extreme conditions or clever configurations, a photon could fold into a particle, a stable, massive entity like an electron? This idea isn't just poetic. It's a real theoretical proposition, one that's hovered at the edge of physics for nearly a century. Let's begin with what we know. Photons and electrons are fundamentally different. Photons are massless, always in motion, and carry a spin of one. Electrons have mass, can rest, and carry a spin of 1/2. Photons cannot be trapped in a box, Electrons can. Photons vanish upon absorption. Electrons persist. They are, by every standard model measurement, distinct species of existence. And yet, some physicists have wondered whether this distinction is an illusion, not because we lack data, but because we may be missing a deeper pattern. Imagine for a moment that a photon could be bent, not by a lens, not by gravity, but by itself through nonlinear field interactions, through the geometry of space-time, or through mechanisms we do not yet understand. What would happen if that photon curled so tightly that it looped back onto itself? You would no longer have a traveling wave. You would have a standing wave, a bound state, a knot in the electromagnetic field. This idea appears in various forms. One of the earliest was the photon ring hypothesis, which proposed that electrons might be photons tracing closed circular paths. In this view, mass arises not from internal components, but from the confinement of energy in space. The same way, energy trapped in a vibrating string gives rise to musical notes. There's beauty in this. An electron would not be a thing made from light, it would be light, shaped. It would explain its charge, its spin, even its magnetic moment as emergent properties of field geometry. But there's a catch. Several, in fact. First, the mathematics of such a configuration is mind-bending. Maxwell's equations, even extended into quantum electrodynamics, do not naturally yield stable, self-confined photon loops. Fields tend to radiate outward. Photons tend to escape. Trapping one within itself without additional forces or constraints remains, so far, unproven. Second, the spin doesn't match. A photon has spin 1, an electron has spin 1/2. This is not a trivial discrepancy. It is embedded deep in the symmetry structure of the universe. In quantum field theory, spin values are not just labels, they determine how particles behave under rotations, how they combine, and what statistics they obey. So far, no known mechanism allows a spin 1 field to spontaneously produce a spin 1/2 particle without introducing new layers of complexity. Third, the standard model of particle physics, as currently formulated, makes no allowance for this kind of transmutation. Photons are force carriers. Electrons are matter particles. They arise from different fields entirely. While both interact via electromagnetism, they belong to different sectors of the quantum zoo. And yet, the allure persists. Because in a world where matter and energy are interchangeable, as Einstein's famous equation tells us, it feels almost inevitable to ask whether the boundary between light and mass is more flexible than we think. There have been experiments that play with the edge of this idea. For example, in high-energy particle collisions, photons can interact with other photons to create matter-antimatter pairs, an electron and a positron. This process, known as two-photon pair production, is real and observable. It requires incredibly high energies, but it shows that light can, under the right conditions, create particles with mass. Of course, in these collisions, the photon does not bend into a loop. Instead, two photons interact in such a way that their combined energy and angular momentum meet the requirements for particle creation. But still, it's a crack in the wall, a hint that light and matter might be two faces of the same entity, briefly trading masks. Another clue comes from the anomalous magnetic moment of the electron, a tiny deviation from predicted values that emerges only when higher-order interactions are included. Some speculative theories suggest that if the electron had an internal structure, a hidden configuration, it could help explain this anomaly. Nothing confirmed yet, but the door remains slightly ajar. Still, mainstream physics treads carefully here, not because the idea is absurd, but because the evidence doesn't demand it. So, why bring this up at all? Because it shows us something about the photon, not just what it is, but what it isn't. If a photon could be reconfigured into an electron, it would require immense precision, perhaps even a new understanding of fields, topology, or quantum geometry. The photon would need to maintain coherence, self-interact, and remain bound in a stable form indefinitely. No jitter, no leakage, no entropy. In other words, for a photon to become matter, it must be perfect. And to even imagine such a transformation, we must accept that photons are astonishingly simple. No gears, no compartments, no secret layers, just field behavior, so consistent and uniform that it could, in theory, be curved into a new kind of existence. Whether this is true or not, the point remains. Photons must be structureless to even qualify for such speculative destiny. They must be the cleanest canvas the universe offers the ground state of action, upon which complexity might one day be painted. So, while mainstream physics continues to define the photon and electron as distinct, this speculative edge, this ghost of possibility, teaches us something profound. That perhaps the simplicity of light is not a limit, but a foundation, a place from which everything else, mass, charge, identity could, in principle, arise. In the next part of our journey, we will pull back again from the speculative edge and return to something very practical. We will ask a deceptively simple question that cuts through every layer we've explored so far. If a photon has no mass, then where does its energy come from? So far, we've peeled back several layers of a mystery that refuses to vanish. The photon, seemingly simple, nearly abstract, has no measurable size, no detectable interior, and no rest mass. And yet, it carries energy. It can trigger reactions, heat surfaces, push particles, even fuel life itself. But if it has no mass, no bulk, no body, where exactly is that energy coming from? This isn't a casual question. Energy is not just some vague concept in physics, it is a currency with strict accounting rules. Every interaction, every collision, every transformation in the universe must balance this cosmic ledger. If a photon imparts energy to an electron, that energy must have come from somewhere. But what somewhere exists inside a structureless, massless ripple? Let's start with what we do know. A photon's energy is not stored in mass. This we've already ruled out. According to Einstein's famous equation, mass and energy are equivalent. But the formula has a second, often overlooked version, E equals pc, where E is energy, P is momentum, and C is the speed of light. This tells us that a photon's energy is tied directly to its momentum, not its mass. It moves, always at light speed, and this movement, this unwavering propagation, is what defines its energetic presence. The moment it stops moving, it ceases to exist. A photon cannot rest. It cannot pause. It exists only as a wave in motion. So, how much energy does it carry? That depends on its frequency. The higher the frequency, the more tightly packed the wave, the more energy each photon possesses. This is captured by another foundational equation of quantum physics, E equals h, where h is Planck's constant and f is the frequency of the photon. This means that gamma rays with extremely high frequencies carry much more energy than microwaves or radio waves. Each individual photon in a gamma ray beam is thousands or millions of times more energetic than one in a microwave oven. But frequency is just how often something wiggles. So now we arrive at an unsettling realization. The photon's energy is not stored inside it at all. It's not locked in a core. It's not compressed into a shell. It is the pattern of the field, how quickly and sharply it oscillates through time. In other words, energy is not something a photon holds. It is something a photon is. This might feel unsatisfying at first. We're so used to thinking of energy as a fuel, something stored inside batteries, or coiled into springs, or compressed into chemical bonds. But in physics, energy is a description of behavior. It tells you how much change an entity can induce when it interacts. So, when a photon strikes a metal surface and ejects an electron, a process known as the photoelectric effect, it's not using up some reserve of energy. It's transferring energy that was encoded into its frequency from the very beginning. The act of absorption is instantaneous. The photon vanishes. The electron jumps. The energy moves forward, never stored, always flowing. But this invites an even deeper question. Where did the photon get that frequency in the first place? The answer lies in how the photon was created. Photons do not appear from nowhere. They are born in transitions when an excited atom relaxes, when a particle accelerates, when a charged object vibrates. These processes disturb the electromagnetic field in specific ways, imprinting the outgoing photon with a frequency that reflects the conditions of its birth. This is why spectral lines, the fingerprints of atoms, are so precise. Each line corresponds to a specific photon energy, which comes from the difference between two energy levels inside an atom. The photon inherits this difference as its own. It carries that energy away, not as weight, not as substance, but as timing, as a rhythm in the field. That rhythm, the frequency, is the energy. There's no reservoir, no center, no tank to be drained. This understanding shifts the whole way we think about particles. The photon is not a thing made of energy. It is an event that expresses energy through form. A pattern, not a pellet. A relationship between space and time, not a building block in the classical sense. This also explains why photons do not decay. A free photon, moving through vacuum, will never get tired. It will not lose energy or slow down unless it interacts with something. Its frequency, and thus its energy, is perfectly preserved unless the universe itself stretches beneath it. And this, too, happens. In cosmology, we see that light from distant galaxies is redshifted, stretched to longer wavelengths by the expansion of space. As the universe expands, the wave crests spread apart, and the photon's energy decreases accordingly. It is not that the photon is aging or eroding. It is that space itself is changing the scale of the field's rhythm. This might be the closest we ever get to seeing a photon lose energy, and even here, it is not a loss in the traditional sense. It's a consequence of context. The photon has not failed. The universe has simply changed around it. In a way, the photon is more transparent than anything else in physics. Its behavior is fully exposed. No hidden compartments, no complex machinery, just a simple, unyielding relationship between field, frequency, and motion. Its energy is not a possession. It is a wave's heartbeat. And yet, for something so minimal, it is astonishingly capable. That energy can warm your skin on a sunny day. It can power photosynthesis in plants. It can trigger mutations in DNA. It can be encoded, beamed, and decoded across the stars, all without ever having a surface, or a core, or a resting point. So once again, we arrive at an answer that is also a doorway. The photon has no mass. It has no inside, but it has frequency, and that frequency is energy. No containers, no fuel tanks, just motion, perfectly encoded. But this raises another paradox. If energy is tied to frequency, and frequency is tied to wave behavior, does this mean the photon has a size, a length, a shape? In the next part of our journey, we ask a question that might challenge everything you think you know about space and form. Does a photon have a size? And if so, how can we ever measure it? By now, we've grown familiar with the photon's peculiar qualities. No rest mass, no measurable structure, no interior, and yet energy, spin, momentum, purpose. But here comes a question that lingers in the shadows. Does a photon occupy space? Does it have a size, a length, a shape? It's a question that seems so simple a child could ask it, and yet so complex that physics still wrestles with how to answer. Let's start with the obvious. If you try to see a photon, you'll find nothing. You cannot photograph one in flight. You cannot trap one in a cage and measure its diameter. Even if you send it through a slit or bounce it off a mirror, all you ever detect is where it interacted a point, a pixel, a flash. From that, one might conclude, aha, the photon must be point-like, no size at all. But this conclusion hides a mistake, one that collapses two different ideas: interaction and existence. Yes, photons interact at specific points. When a detector clicks, it does so in one place. But this does not mean the photon always existed only in that point. In quantum physics, particles are not where they are detected. They are described by probability amplitudes wave functions, which are spread out, continuous, and fuzzy until the moment of measurement. A photon, before it is absorbed, behaves as a delocalized excitation of the electromagnetic field. It can interfere with itself, diffract through slits, reflect and refract along multiple paths at once. All of this points to a spatial extent, a region over which the photon is. But how big is that region? That depends on what you mean by size. Let's consider a common laser, a red pointer. Each photon it emits has a wavelength of about 650 nanometers. That's the distance between peaks in the electromagnetic wave, a physical length. So one might be tempted to say, the photon is 650 nanometers long. But this, too, is a simplification. Wavelength tells us about periodicity, not size. It describes the rhythm of oscillation, not how many cycles the photon spans. A photon could be a short pulse or a long one. It could be tightly localized or widely spread. It depends on how it was created. In fact, the more precisely you define a photon's frequency, the less precisely you can define its position, a consequence of the uncertainty principle. Sharp energy, fuzzy location. Sharp location, fuzzy energy. So in one sense, a photon's size is indefinite, a trade-off between temporal duration and frequency spread. The more you squeeze one parameter, the more the other expands. This is not a bug in the math. It is a fundamental feature of quantum fields. In practical terms, photons often extend over many wavelengths. A single photon, emitted by an excited atom, might have a coherence length, a kind of effective size of tens, hundreds, or even thousands of wavelengths, depending on the environment. That means it could stretch over microns or millimeters. But what does that mean physically? It means that the photon isn't localized the way we imagine tiny things to be. It's not a marble. It's not a sphere with borders. It's a mode of the field, a wave packet that moves through space with a defined momentum, frequency, and polarization, but with an inherently fuzzy footprint. Even more strangely, this footprint doesn't behave like an ordinary object. If you send a single photon through a beam splitter, a half-silvered mirror, it can be found emerging from either output port, but never both. Over many repetitions, a pattern emerges. The photon acts like a wave until it is measured, at which point it chooses a location and registers a click. But no matter how far apart the detectors are, the photon is always observed in one place. So, again, no definite shape, no classical path, only a pattern of probabilities encoded in the structure of the electromagnetic field. This is why asking for the size of a photon can be misleading. You are not asking for the diameter of a marble. You are asking, over how much space does this excitation live before it dies? And the answer depends not on the photon itself, but on its context. What generated it, how coherent it is, what conditions it passed through. What you're trying to measure, this contextuality is hard to accept. We want a clean answer: the photon is X nanometers long. But nature doesn't give us that. It gives us a spectrum of possibilities, bounded by uncertainty, shaped by interaction, and governed by fields that do not fit into tidy containers. To make this concrete, imagine the following. You have a photon with a well-defined frequency, say, green light at 550 terahertz. The corresponding wavelength is about 550 nanometers. If the source emits a pulse lasting just one oscillation, then the photon might span something close to that length. But if the emission lasts for 1,000 cycles, the photon could stretch over hundreds of microns. Now ask yourself, has the photon changed? No. Only your description of it has your resolution, your definition, your measurement window. The photon remains a ripple in the electromagnetic field, a burst of energy with frequency and spin, not a ball with borders. And yet, despite this fluidity, it behaves with exquisite precision. It can trigger a receptor in the eye. It can deliver a precise momentum transfer in a quantum experiment. It can interfere with itself across vast distances. How can something so fuzzy be so exact? This is one of the core paradoxes of quantum field theory, the union of uncertainty with stability. The photon, like other quantum particles, does not need to have boundaries to have identity. It is defined by how it interacts, not by what it is made of. And so, once again, The photon teaches us a kind of humility. It refuses to be boxed. It refuses to be weighed. It refuses to play by the rules of common intuition. Its size is a relationship between events. Its shape is a probability cloud. Its presence is a question of coherence and context. So, the question, does a photon have a size, is better rephrased as, over what region of space and time does the photon's influence exist before it ends? And to that question, we can only answer, it depends. But perhaps that's the wrong question altogether, because now we must ask, if the photon is so minimal, so pure, is it the simplest unit of energy the universe allows? Or could something even simpler exist? In the next part, we explore that frontier. Is the photon truly the indivisible quantum of light, or just a messenger of something deeper still? The more we study the photon, the more it begins to feel like a paradox wrapped in clarity. It is massless, yet energetic, without shape, yet directional. It can carry angular momentum, yet has no spinning parts. It touches everything, yet reveals almost nothing about itself. So now, standing here at the edge of what we know, we must ask, is the photon the most fundamental quantum of energy nature permits? Is it the bottom layer of the pyramid, the irreducible bit from which light and all electromagnetic phenomena emerge? At first, the answer seems obvious. In quantum electrodynamics, our best theory of how light and matter interact, the photon is the elementary excitation of the electromagnetic field. You can't break it into halves. You can't open it. You can't dig deeper. The photon is the field's minimal event, a single quantum of action, a click in the great machine. But look closer. There's something strange about how photons behave compared to other particles. Electrons, protons, atoms, these can be counted, labeled, conserved. You can track how many go in, how many come out. They carry identity across time. You can't just make or destroy an electron on a whim. Conservation laws prevent it. But photons? Photons don't follow the same rules. They are not conserved. There's no universal photon number you have to preserve. In the heart of a star, trillions of photons are born and destroyed every second. In a dim room, a single atom can absorb or emit a photon without changing its fundamental state. You can have 0 photons, 1, or a million, and nothing about the charge or structure of the universe has changed. This flexibility makes photons unique. It also raises a possibility. Perhaps the photon is not a thing at all. Perhaps it's more accurate to think of the photon as an action, a temporary bridge between states, an exchange of energy between matter and field. Not a bead passed along a string, but a handshake, something that only exists because it is doing something. If this is true, then the photon is not just the simplest unit of light. It may be the simplest unit of interaction. Let's follow that thread. In quantum mechanics, every measurable quantity, energy, momentum, angular momentum, comes in discrete chunks. You cannot absorb half a photon. You cannot emit a third. You either make the jump or you don't. This discreteness is not a property of the photon alone. It is a property of the system. When an atom falls from one energy level to another, it releases a photon with exactly the energy difference. The photon is not a stored object. It is the record of a change. So, instead of thinking of the photon as an indivisible particle, we might think of it as a quantized event, a manifestation of how the electromagnetic field responds to change. No internal clockwork, no scaffold, just a transition written into spacetime. In this way, the photon is not just simple, it is almost abstract, and yet it's real. We build technology on it. We decode its messages from stars and galaxies. We manipulate it in labs with stunning precision. So, what makes it feel so elusive? Perhaps it's because the photon doesn't leave tracks. Electrons can be traced, protons can be confined, but photons, they arrive, and then they vanish. No residual, no footprint. Unless they interact, they are invisible not just to the eye, but to every detector. We only know a photon was present because something changed. This is why photons often feel like messengers, not participants. They mediate force, they carry influence, but they do not hold properties in the same way matter does. And this brings us back to our question. Is the photon the simplest quantum the universe allows? In one sense, yes. It's the lowest energy unit of electromagnetic action. It's indivisible. It requires no supporting structure. It is born directly from symmetry, specifically from the gauge symmetry of the electromagnetic field. In physics, that kind of purity is rare. But there are hints, subtle ones, that even this simplicity might be hiding something deeper. In quantum field theory, there is a concept called the vacuum state, the lowest energy state of a field, seemingly empty, but not truly void. Even in this so-called vacuum, fields fluctuate. Virtual particles appear and vanish. Photons flicker in and out, not as real quanta, but as mathematical contributions to interactions. Here, photons are no longer discrete units. They are part of a restless sea, an ocean of potential. Some interpretations suggest that what we call a photon is just a coherent pulse rising briefly from that sea, a whisper in the fluctuations, a pattern that momentarily stands out. If that's true, then the photon may not be a thing at all, not in the traditional sense. It may be a momentary crest in an infinite wave, a structureless rise, a flicker of pure potential, frozen long enough to deliver energy, momentum, and spin. No gears, no edges, just form. This is not to say the photon is unreal. Quite the opposite. Its effects are undeniable. But it may not be the starting point of nature. It may itself be emergent, a byproduct of deeper laws, deeper fields, deeper symmetries that we have only glimpsed. And this changes the question again. Perhaps instead of asking, is the photon the simplest particle? We should ask, is it the most necessary one? A bridge, a communicator, a spark, not a building block, but a signal, a message passed from one part of the universe to another. No storage, no delay, just delivery, and then gone. So now we turn our eyes to where the photon travels. What happens to it on its journey through the cosmos? Because photons do not just live in labs or lasers, they race through interstellar voids, skim black holes, pierce clouds of plasma, and arrive at Earth carrying stories billions of years old. In the next part of our quiet exploration, we'll ask, what do the most extreme environments in the universe tell us about the photon's true nature? And why, despite traveling across time and space, photons still refuse to show us what they're made of? If there's one thing more revealing than a controlled laboratory experiment, it's the chaos of the cosmos. Here on Earth, we generate photons in clean rooms and quiet chambers. We control temperatures. We isolate vibrations. We prepare neat pulses of light and send them through polished lenses. But the universe doesn't work like that. Out there, photons are born in collapse and collision. They are forged in supernova shockwaves, in the scorching mouths of quasars, in the blinding flash of gamma-ray bursts. They travel for billions of years across expanding space, skimming past neutron stars, threading through gravitational wells, slipping between plasma filaments of galactic gas. If anything could shake loose a secret from inside a photon, it would be this. So, what do we see? We see consistency, photons, regardless of how violently they're born or how far they travel, remain identical. Whether they come from a distant galaxy or a dying star, from the early universe or a backyard laser, they all follow the same rules, same spin, same zero rest mass, same quantum statistics. They behave with the precision of a law etched into the geometry of existence itself. Let's take a concrete example, the photons of the cosmic microwave background. These particles, billions of them, have been streaming through space since the universe was just a few 100,000 years old. That's more than 13 billion years of travel. Along the way, they've passed galaxies, dark matter halos, magnetic fields, and immense voids. And yet, when they reach our detectors, they still exhibit a near-perfect blackbody spectrum with a temperature uniformity measured to better than 1 part in 100,000. That uniformity shouldn't be possible if photons had a structure that could degrade. Imagine a paper airplane thrown across a city. Now imagine it's still crisp and untorn when it lands. Now multiply the city to the size of the visible universe. That's what these photons have done, remained untouched across unimaginable scales. Or consider gamma ray bursts, the brightest explosions known. These events can outshine entire galaxies for a few seconds. The photons they emit, often in the form of high-energy gamma rays, travel across vast swaths of space before reaching our telescopes. If photons had any composite parts, if they were made of smaller constituents that could rattle or shift under extreme acceleration or dense gravity, we'd see distortions. We'd see blurring, energy loss, changes in arrival time across different frequencies. We don't. In fact, some gamma-ray photons of different energies have arrived on Earth just nanoseconds apart, after journeys of billions of years. The Fermi Gamma-ray Space Telescope has measured this with exquisite precision. The conclusion? No evidence of dispersion, no delay based on energy, no breakdown of photon behavior under pressure. This places enormous constraints on any theory suggesting that photons are made of parts or have substructures that reveal themselves at high energies. If photons had an interior that could flex, stretch, or even exist as twisted bundles of field, we'd expect high-frequency photons to behave differently over time, to break formation, to split, to decay. But across the heavens, they don't. Even near the most intense gravitational warping in the universe, black holes' photons remain obedient. They bend, yes, their path curves under the influence of space-time, but their identity remains untouched. They enter as photons. They leave, if they can, as photons. Their fields may redshift, stretched by the gravitational gradient, but this too changes only their frequency, not their structure. The photon does not unravel, it does not dissolve. This tells us something remarkable. If the photon has a structure, it must be unimaginably simple, so simple that even the furnace of stars, the density of neutron cores, and the cold silence of intergalactic space cannot disturb it. But there's another piece to this cosmic puzzle. We also observe photons through interference, the way their waves add and subtract, creating patterns. These interference patterns can persist even across astronomical distances, telling us the photon retains coherence, a kind of quantum memory of its phase and origin. That's astonishing. Think about what it means for a photon to remember where it came from, even after billions of years and countless gravitational encounters. It means the field excitation that defines the photon is not disturbed by the passage of time or by the journey across space. If photons were complicated, they'd lose that coherence. If they were turbulent or had internal variability, the pattern would blur. Instead, we see clarity, overwhelming clarity. It's as though photons were designed to be pure messengers, no baggage, no drift, just signal. And this is perhaps the most compelling argument against internal structure. Not because we haven't looked hard enough, but because the universe itself has conducted the experiment for us at scales, energies, and durations we could never replicate. The result? Photons do not fall apart. They do not mutate. They do not age in any measurable way. They are timeless events, carrying energy from one place to another without ever revealing how they carry it. They slip through cosmic turbulence like needles through silk, precise, unfrayed, untouched. This consistency is not just beautiful, it is instructive. It tells us something about the universe itself, that at its most foundational level, there may be principles so simple, so symmetrical, so unbreakable, that no amount of time, heat, or pressure can corrupt them. The photon may be our best clue to what those principles are. But of course, the universe rarely answers a question without posing another, because while photons do not age, they do interact. And every time they do, we see something even stranger. Sometimes they behave like waves. Sometimes they behave like particles. Never both. Always one or the other, depending on how we ask. This leads us to the question that first haunted Einstein, that puzzled Bohr, and that still baffles students and physicists alike. How can something with no parts behave as both a wave and a particle? And what does that duality say about the photon's true identity? In the next part of our slow journey, we enter the heart of quantum weirdness, not with drama, but with care, and ask, why does light behave like a wave until you ask it to be a particle? And how can such a contradiction arise from something with nothing inside? It's one of the most whispered paradoxes in science. You'll find it scribbled in textbooks, muttered across coffee tables, danced around in TED Talks, and invoked any time someone wants to make physics feel mysterious. Light behaves like both a wave and a particle, and the photon, that tiny carrier of light, is caught at the center of this contradiction. We've already peeled away its outer assumptions. No rest mass, no internal parts, no measurable shape. We've accepted that it is not a tiny marble made of light stuff, but a ripple, a brief excitation in the electromagnetic field. So it should behave like a wave, right? Spread out, interfering, bending, and blurring. But then we detect it, and it arrives not as a soft splash, but as a point. One click, one spot on the screen, a single electron ejected, a grain of film blackened, a nerve cell in the retina firing, and then nothing. That's the essence of the paradox. Light travels like a wave, but lands like a particle. Let's walk through it. Suppose you fire a single photon at a barrier with two slits. Classic experiment. The wave function of the photon spreads out. It doesn't choose a slit. It passes through both slits, interfering with itself, creating a pattern of highs and lows, ripples of probability. But the moment it reaches the detection screen, it appears as a dot, a pixel. One place, not two, never in between. But do this experiment again, and again, and again. The dots start to form a pattern, an interference pattern, just like you'd expect from a wave. Which is it, then? The photon is never both a wave and a particle at the same time. It is either, depending on how you look, depending on what you ask, depending on what kind of measurement you perform. This is not a failure of the photon. It is a failure of our categories. When you think of wave and particle as opposing metaphors, as things that cannot overlap, you create the paradox. But nature doesn't care about our metaphors. Nature just does what it does. Quantum field theory tells us the truth in mathematical terms. The photon is a quantum excitation of the electromagnetic field, and quantum excitations do not live comfortably inside classical ideas. They are neither waves nor particles in the traditional sense. They are quantum objects, and that means their behavior depends on context. A photon does not have a position until it is measured. It does not travel along a definite path. Its trajectory is not a line through space, but a probability amplitude, evolving over time. When not observed, the photon exists in a superposition, a blend of possibilities. When observed, it collapses into one outcome. This collapse is not violent. It's not dramatic. It's just an interaction. A photon hits a detector. The wave function changes. The possibility becomes fact. And here's what makes the photon so profound. It's the perfect vehicle to reveal this quantum behavior because it has nothing inside to hide behind. You can't blame internal chaos. You can't blame hidden mass. You can't even blame thermal noise. The photon is clean. It is simple, and yet it behaves with a strangeness that refuses to disappear. This is why light has always played such a pivotal role in our understanding of quantum theory. It was the photoelectric effect, where Einstein showed that light must come in discrete packets, that helped launch quantum mechanics in the early 20th century. It was double-slit interference with single photons that revealed the breakdown of classical logic. It was entangled photon pairs that helped demonstrate the reality of quantum non-locality. Every time we probe light more deeply, it teaches us the same lesson. Reality does not behave as expected when you ask precise questions. Let's get even more specific. The wave behavior of light comes from its ability to interfere, to cancel, and amplify across space. This comes from the field's spread, the way it occupies multiple paths at once. The particle behavior comes from its quantized interaction, the way it transfers energy and momentum in discrete jumps. Both are true, but only one is visible at a time. This is not because the photon switches masks. It's because we do. Measurement is not just passive observation, it's participation. To measure a photon is to interact with it, and interaction defines outcome. This is what physicist Niels Bohr called complementarity, the idea that different experimental setups reveal different, mutually exclusive aspects of a quantum system. You can't measure both the wave and the particle simultaneously, not because of technical limits, but because these properties do not coexist in a classical sense. They belong to different questions. So what does this mean for our understanding of what a photon is? It means we must abandon the hope of classical identity. We must accept the photon as a quantum event, a structured pattern in a field, whose full nature is only revealed when interacted with, and whose behavior depends entirely on the context of that interaction. It is neither a wave nor a particle, but something more abstract and universal, a carrier of energy, a messenger of momentum, a moment of correlation between emitter and absorber. It is not a thing in the way a baseball is. It is a possibility made real by contact, and that contact, that interaction, is the only time we ever truly see the photon. Everything before that is uncertainty, is potential, is wave function, so we are left with a picture that is simultaneously empty and full. The photon has no core, no volume, no moving parts, but it carries action, it triggers change, it connects one event to another, and perhaps that's the deepest truth we've uncovered so far. The photon is not an object, it is a process, not a piece of light, but the act of light happening, and yet, for all this abstraction, the photon still fits inside equations, still lands on our skin, still bounces off glass, still burns paper, still reaches across the cosmos and into our telescopes. So what are we left with? A final question, a question of language, a question of reality. If all our metaphors fail wave, particle, point, pulse, then how should we describe the photon? In the final part of this journey, we gather everything we've seen, every paradox we've touched, and arrive at a conclusion as soft as it is precise. What is a photon really according to the best physics we have? And why might that answer be the most humbling one of all? We've walked with the photon through nearly every contradiction it holds, and still, it floats beyond our grip, a thing with no interior, no edges, no mass, but with spin, energy, direction, and influence, a ripple that never settles, a messenger that never rests, a presence made entirely of motion, but with no substance underneath. So now, at the end of this slow and careful journey, it's time to ask the question directly. What is a photon? Not metaphorically, not poetically, but in the clearest terms physics can offer. Here it is. A photon is a quantum excitation of the electromagnetic field. That's the official answer. It's deceptively simple, only 7 words, and yet behind each one hides a century of progress, confusion, revolution, and clarity. Let's unpack it slowly. Quantum excitation. This phrase carries profound implications. Quantum means that the field in this case, the electromagnetic field, cannot change its energy in smooth, continuous amounts. It must do so in discrete steps, jumps, packets. An excitation is one such packet. It's not a thing sitting inside the field. It is the field, briefly configured in a special, quantized way. A spike, a wave, a blip in time and space, consistent with all the field's symmetries and laws. This excitation is what we call the photon. But this thing we name has no parts, no shape, no shell. It's not made of something. It's what happens when the field expresses itself at its smallest unit. There is no core to cut into. There is no blueprint underneath. Just behavior. Just interaction. Just effect. A photon doesn't exist in the way a rock exists. It occurs of the electromagnetic field. This tells us what kind of field is being excited. In modern physics, every type of fundamental particle corresponds to a field that pervades all of space. Electrons arise from the electron field, quarks from the quark fields, the Higgs boson from the Higgs field, Photons come from the electromagnetic field, a structure that exists everywhere, even in perfect vacuum. This field is not electricity or magnetism. It's the unified foundation that gives rise to both. It can vibrate, it can store energy, and when excited in the smallest possible way, when it ripples, just once, in just the right configuration, it becomes a photon. This ripple is what carries light. This ripple is what warms your skin. This ripple is what transmits radio signals and burns the Sunday. So, what is a photon, really? Not a particle, not a wave, not a duality. It is a unit of interaction, an event, an indivisible bridge between emission and absorption, between past and future. A photon is what happens when energy moves not through substance, but through field. It is the minimum transaction the universe allows, written in space-time, expressed with precision, and then just as quickly gone. And that's perhaps the most profound thing to understand about photons. They do not persist. They are not conserved. They are not stored in the bank of the universe. They appear and disappear in perfect alignment with energy conservation, momentum conservation, and the structure of quantum fields. They are pure happening, not presence. Does this mean photons are not real? No, quite the opposite. Photons are among the most precisely studied phenomena in all of physics. We measure them, count them, control their polarization, direction, energy, spin. We create them on demand in laser labs and detect them in billion-dollar telescopes pointed at the stars. They follow rules so tightly that deviations are measured to 1 part in a trillion. If anything, photons are too real, so real, in fact, that they've exposed the limits of our categories. They've shown us that the universe is not made of tiny, solid things. It is made of relationships, of correlations, of fields expressing themselves in quantized action. Photons are the purest form of this action we know. They are what changes look like when that change happens electromagnetically. So what can't a photon do? It can't rest. It can't carry a memory of its own past. It can't be cut in half. It can't live outside of motion. And it can't tell us, finally, what it's made of, because that question no longer applies. Instead, we ask, what does the photon mean? It means the universe has structure even in vacuum. It means the laws of motion, interaction, and time exist even when nothing solid is there. It means that light is not a stream of particles, but a sequence of events, field excitations moving at a universal speed, delivering energy from one point to another, without ever carrying mass, size, or shape. It means that reality can happen without things. And why should we care? Because photons are not just cosmic trivia. They are the reason we see. They are the only messengers that have touched both the early universe and our eyes. They power solar systems, enable communication, trigger photosynthesis, reveal atoms, define chemistry, and they do all this while remaining untouchable, never at rest, never decaying, never breaking down. They are the language of the cosmos, whispered in a dialect made only of motion and change. So, what is a photon? A photon is the universe choosing to express energy, nothing more, nothing less. It is not a thing. It is not a piece of light. It is the act of light itself. And maybe that's all we ever needed to know. Final note. You've now walked through the most elegant nothing we've ever discovered. A thing that isn't a thing. A presence that only exists when it interacts. A message without a message bearer. A wave with no water. A particle with no substance. A moment that changes everything and then is gone. Please like and subscribe, because this journey will change how you see our place in the universe. Prepare yourselves. We begin again with the light,